Now, ladies and gentlemen, we'll kick off GYSS 2024 this morning with the opening plenary by Professor Martin Green, 2022 Millenium Technology Prize winner. He will be speaking on the topic solar photovoltaics, recent developments and role in climate change mitigation. The Q&A session will be moderated by Professor Annalisa Bruno from the Nanyang Technological University. Professor Green, please.
Your Royal Highness and other distinguished guests and speakers, and of course, global young scientists. It's a great honour for me personally to be asked to speak to you this morning on a topic that's very near and dear to me, solar photovoltaics. Particularly recent developments and the way I believe it's going to have a major impact upon climate change mitigation. As mentioned, I'm with the University of New South Wales in Sydney, and you can see the iconic Sydney Opera House there, and our facilities, in research facilities and technology transfer facilities at the university in the lower right-hand corner. So the talk's got a very simple outline, so there'll be three segments to it. First off, I'll talk about the technology, then I'll talk about the costs, and then finally about the role I see for photovoltaics in climate change mitigation. So solar cells are very much a technology of the 20th century. So it all started with Albert Einstein and his realization that light, when it interacted with matter, could be regarded as particulate, overcoming the well-established demonstration in the 19th century that light was in fact a wave. And this was really important on a number of fronts for photovoltaics because it triggered the development of quantum mechanics, the understanding of the properties of silicon and, of course, of light itself. So the photons have a color, and the graph on the upper right there just sort of shows the energy distribution of the photons within the sunlight. So the colored region shows the regions the eye responds to, and along the top there's a line showing the energy of the photons. So the energy of each photon is quite small. It's measured in electron volts, which is a really small unit of energy. So around 1 to 3 electron volts, most of the photons have energy in that range. It's a very convenient unit because a solar cell, actually its role is to convert a photon into an electron. And the number of electron volts involved with the photon energy gives you an idea of the voltage that can be converted in that conversion. Energy conversion prevents you from generating more voltage than the electron volt rating of the photon. So this is a solar cell, just a brief outline of the operation. Photons with enough energy enter a semiconductor. This is a silicon cell sketch that's shown there. And those with enough energy will promote electrons in atomic bonds to high energy states where they're mobile through the material. They leave behind a vacant state, and it's sort of mobile as well in that neighboring electrons in related states can move into that state. So it's like a bubble moving through water. The whole can move around at the ground state energy, and electrons in this excited state can also move. So to do something useful with that process, you need to get the electrons moving off in one direction and the holes to be moving off in the other. And that's where the design of the solar cell comes into play. By introducing impurities into the silicon, you can introduce an asymmetry. In one direction, it's easier for the electrons to go, and the other direction, it's easier for the holes to go according to the impurities that you introduce. So in this cell, it's designed that it's easy for electrons to go upwards, holes to go downwards, so the electrons go up. You connect a load between the top and the back, you get a current flowing through that load and energy getting dissipated in the load. And the maximum voltage that a cell like this can generate depends upon the energy of the lowest energy photon that can be absorbed. So a silicon cell absorbs photons with energy above 1.1 electron volt. So the maximum voltage you can get from a silicon cell is 1.1 volt. You know, that's just from conservation of energy. And then other realities involved in cell operation reduce you down to a fraction of that, somewhere around about 70% of that voltage. The silicon used in these cells is now made really thin. So about a sixth of a millimeter in thickness, so really very thin, and are quite brittle as a consequence. So they get encapsulated into what's called a solar module, where a glass cover sheet provides mechanical support along with generally aluminium frames. So they provide the structural support to provide mechanical protection of the cells. And then everything's encapsulated very tightly into a laminated package. And that also provides chemical protection of the cells, prevents exposure to excessive amounts of water and other possible atmospheric contaminants, and also provides electrical protection in that these cells can be used in systems that generate thousands of volts. So you need to protect, protect people in the environment from the voltages that they're capable of generating. So it provides mechanical, electrical, and chemical protection of the cells. These modules have been getting bigger. So this just shows a transition from about 2015 up to the present. And that gentleman there is 6 foot tall. You can see how the growth, the module's growing. Modules with square cells in them, like on the left there, are old-fashioned modules. Now modern modules have rectangular cells. So the voltage output from a cell is limited by the energy of the photon. So, you know, 1 EV is the type of, 1 volt is the sort of type of voltage each cell will generate. But that's not very useful. You want more voltage, so you connect a lot of cells in series as shown here. And but the current generated by a cell is quite enormous because it just depends upon the number of photons getting absorbed, which is gigantic. And by cutting the original wafers into half, you can increase the size of the original wafer, and that's why the industry has now gone to rectangular cells. And the cell on the far right there, you've got a front view as well as a back view. So nowadays, the modules are designed so they can convert light from either direction, because you get a lot of stray light falling on the rear, so you get this extra boost in output. So that big module there generates under bright sunlight power equivalent to 1 horsepower. So it's about the same length as a horse, about 8 foot or 2.4 meters long, about the same surface area as a horse, but only 20 or 30 times lighter in weight than a horse. So you can generate quite a reasonable amount of power from these, as you can imagine. Every large panel equivalent to a horse in its power generation. The first efficient silicon cells, it depended upon the development of quantum mechanics and then of silicon technology, before the first efficient cells were made, and that was in 1953 and announced in 1954. They're the gentlemen involved on the left there. And perhaps appropriately, considering the role, I believe, that solar cells are going to play in mitigating climate change and in providing energy for the world in the future, made front page news on the New York Times. So a little article there on the front page. And there was a lot of excitement about ways that this technology could be put to work, with the family up there, admiring the solar panel. But back then, the costs of the cell was just enormous. So far too expensive to be used for household use, for example. But there was an almost immediate application found on spacecraft, where costs weren't so important. The weight of the power source was more important than the costs. And the solar cells were mounted on the 4th satellite to go up internationally in 1958. And when communication satellites started to be brought in the 1960s, solar cells were the preferred choice for the cells. And there, the high cost associated didn't really mitigate against that use. So an industry got built up providing these cells for satellites. And the little chart at the lower bottom there just sort of shows the early evolution of the efficiency of the cells. So it started about 1% efficient back in the early 1940s, and the big jump with this work at Bell Labs took them up to 6% efficiency, and then upwards and upwards as developed in the space program up to about 15%. And then in the early 70s, when I joined the field, another jump in efficiency at ComSat Labs, a lab specifically set up to improve spacecraft technology. They gave another boost to performance. So the cell in the upper left there shows the structure of a cell that reached close to 17% efficiency. So two things are done there, different from the previous drawing I showed. One is the pyramids on the top, and they're formed from crystallographic planes in the single crystal silicon that's used for these cells. So it's just intersecting 111 crystallographic planes in the silicon material form those pyramids, almost the same geometry as the big pyramids at Giza, but of course a lot smaller. And then at the back you can see that region labeled P+. That's a region where extra impurities have been added, aluminium in this case, to make it even harder for electrons to go in that direction. You want them to go up. So that blocks them from going to the back. And so that cell was developed for space, but very quickly a simpler way of applying the metal contacts by screen printing, the way that you often put patterns onto T-shirts and things, was applied to solar, giving a much lower cost way of making the cells. So in the 1970s, with the oil embargoes of that era, there began to be a strong interest in developing cells for terrestrial use, trying to get the costs down from the enormous levels there down to something more manageable for terrestrial application. I don't think anyone realized just how low in cost they would become back then, but we thought they could become low enough to do something useful. And that cell, which was used the pinnacle of technology in the early 70s, became known as the aluminium back surface field cell. And very important historically in that it was the dominant technology for the next 40 years, up until about 2015. Around this time, I'd finished my PhD in 1974 and got a job at the University of New South Wales, and here's me with my first PhD student. We weren't particularly well set up for photovoltaic research, but we're just very fortunate in the work that I'd done for my PhD provided another way of getting this directionality into the cell apart from introducing impurities into the silicon. And that was by using tunneling through thin oxides on the silicon surface. So very fortunately for us, NASA had started a big program to improve silicon cell efficiency, and they believed that could be done by improving the output voltage higher. So I said before, 1 volt sort of the limit, and this is what people were actually getting in the late 70s, 640 millivolts. So less than 60% of that limit determined by the energy conservation. So NASA had a program with a lot of US contractors. We initially weren't part of that program, but we beat all the contractors, even though we had very simple equipment, as you might deduce from that photo there. We were able to make devices, test structures, that were able to beat the best NASA cells and those from their contractors, which sort of gave us an international profile. And that was very helpful in developing the group and getting international funding and so on. Eventually we got NASA funding, and you can see we took the voltage up to close to 700 millivolts, so getting closer to the basic thermodynamic value. One of the structures we developed was quite important there. We were using metal, tunneling between metal and silicon through this thin oxide. At high temperatures, the metals involved would attack the oxide and eat through them, so they weren't very durable if you heat them above 300 degrees or whatever, which you might want to do in some of the cell processing. So we developed this structure where we replaced the metal by doped polycrystalline silicon layer, and that's now known as TOPCon and is one of the current contenders for market dominance within the industry. So with that huge voltage advantage, we realized we had to convert that into an actual performance advantage. So with some of the extra funding we were able to attract because of our increasing international profile, we were able to put together the other equipment we needed to make a sort of state-of-the-art cell incorporating these high voltages, which gave us our first world record in 1983. And that's the small team there that was involved in that effort. And I won't go too much into the technical details, but you can see where, along the top surface of the cell shown in the lower center, we used a thin oxide to provide some of this rectification or directionality to the electron flow. And then the chart on the right just sort of shows the impact our work subsequently had. So when we started, the best confirmed efficiency was 16.5%, independently measured at a test center, and we took that up to 25% over the coming couple of decades. So that's by building on this approach. So 1983 was a very big year for the team in that I did a theoretical paper that sort of showed what would limit the performance of a silicon cell and just sort of identifying some of the features, and it turned out the efficiency limit was much higher than people had previously thought, close to 30% as shown on the chart on the right. And we set a target of getting to 25% as our research goal. And we also looked at cell structures that you could implement that would have the features required to reach that performance level. So one of the ideas that was suggested there, built on something I'd earlier mentioned, was just making small area metal contacts. So rather than using these tunnel structures, make small area contacts, as well as the tunneling structures were the ideas suggested there. So our next cell record, we actually moved away from the tunneling structures to the second idea, small area contacts. We got that at the end of 1983. And I also suggested the drawing in the upper left there, which is now known as the PERC cell. I won't go into what the acronym means. It wouldn't mean much anyhow. But that turned out to be very important as it was the vehicle for us improving the efficiency further. So this is the team by then had grown, and this is the team that made the first 20% efficient cell in 1985. A certain gender imbalance, but we were joined by the females on the right there, who played a big role in the development of this PERC technology to its full potential, which took us right through to the 25% efficiency. So many of these people in that photo went on to play a major role in the development of the industry, as we'll soon see, particularly Awa Wang and Ximin Dai, who's shown there on the right, who became founders of two of the companies that were set up in China to build up the industry. So what's happened since then? Our PERC cell, when we got to our 25%, we said, well, we got to our target and we started moving on in other directions. But that record stayed for 15 years. And then more recently, the record has been improved to just before Christmas, one group reported 27% efficiency, which is now where the technology is. And the efficiency limit, as I mentioned, deduced was between 29 and 30%, and 29.4 is the current sort of precise value that's given to that limit. On the right there is shown 4 structures. So the top one is the PERC cell that I briefly mentioned. It uses this idea of small area contacts to improve the voltage output of the cell, essentially. And the second one goes back to that tunneling idea that we pioneered even earlier before that got us our first world record. The third structure is a lower temperature structure called the heterojunction cell that relies on layers that are deposited at much lower temperature, but again uses this idea of thin intervening oxide or amorphous silicon layers to get the separation of the contacts from the material. And then finally, the structure that presently holds the world record, 27.1%, is a structure where you put the both contacts on the rear. And you can do that with any of the previous technologies as a technique for making those contacts, and companies are investigating all combinations of those contacts for making that structure, but presently holding the record and likely to be the vehicle for taking us to even higher efficiencies. In terms of market share, this shows what's happened, though. So the bars represent 100%, and the maroon and blue regions that dominate to the left are that technology I mentioned earlier, the back surface field technology that dominated for 40 years up to 2015, when the yellow and brown regions started taking over. And that's the PERC technology entering production. And you can see the transition from just about 0 market penetration to 100 happened very quickly. And the reason for that is the photovoltaic industry has been growing very quickly. So manufacturers are installing the best and latest and greatest technology. And if the industry is growing quickly, it means you can quickly displace the incumbent technology. So the industry is doubling in its output every 3 years as a rule of thumb. And so within 3 years, if all the new capacity you're installing is the new technology, you're up to 50% market share, roughly speaking. So that's what's happening. So PERC has dominated up until recently, and this goes up to 2022. Still waiting for the official 2023 results, but that orange region at the top is the second structure there, using our tunneling approach, the TopCon approach. And it's likely to have a much larger market share this year and perhaps make the same rapid takeover of the market as we saw happen with PERC. So longer term, can you do better than this 29.4%? I think the industry will get quite close to that into manufacturing with the silicon cell. But there are approaches to getting beyond that. And the most likely approach to be used is simply stacking cells of different materials on top of one another. So I mentioned before the cells were a photon converter, and the voltage you got out of the cell depended upon the lowest energy of the photon you're converting. So if you stick cells that have a higher, that can convert high energy photons on top of a stack, they'll convert the higher energy photons in the same way a silicon cell would, but give you a higher output voltage. So you stack cells on top of one another, you get this automatic filtering of the sunlight that is really a great feature of the approach. And no one had to design it, it just happens naturally. But the sunlight falls on the cells on the top that respond to the high energy photons. The lower energy photons, it looks transparent to, in the same way as glass is transparent to most photons. So the low energy photons just go through to the next cell in the stack. It absorbs the highest energy ones left, and then the remaining goes through to the bottom cell. So you get this automatic filtering where the photons end up in the right cell. And because the cells on top of the silicon cell are generating a higher voltage, that means you get more energy output than you would if you just stuck with the silicon cell. So the chart on the right just sort of shows how much more energy. So just showing the output as you increase the number of cells. So silicon, as I said, the limit is 29%. That's the green bar shown on the left there. The red bar shows, the ideal, the best you could do with any idealized material, and that's 33%. So the silicon's quite close to that fundamental limit. It's not a bad choice for a single cell. But once you start stacking cells on top of one another, the silicon gets even better in terms of its limiting performance compared to the best possible. So, it's not a bad material to stack cells onto, and commercially speaking, because the industry is so large, making silicon cells, stacking onto silicon is a really sensible market entry strategy. The real problem has been, what material can you stack onto silicon that has all the desirable attributes of silicon? So there's 4 of them that are really important. Like silicon's really abundant, after oxygen, second most abundant in the Earth's crust. It's non-toxic, produces very stable cells, and it gives high efficiency, over 20%. Even though there's over 10,000 semiconductors that are known and been identified and some knowledge of their properties, only 7 have given over 20% efficiency. So it's quite a limited selection from that pool that have given that high efficiency. So that tends to be a fairly severe selection criterion. So one that has is perovskites that many working in photovoltaics would be familiar with. So they have given over 20% efficiency. They involve, they can involve materials that are abundant, but the issue is 30% lead at the moment, which of course is one of the more toxic heavy metals, and stability is nowhere near where it needs to be for a viable commercial product. Organics also get a couple of ticks there, in those 4 categories. So as you can see, as you work through the list there, the other shown there is what I call synthetic silicon. By combining elements in the periodic table in the right proportions, you can synthesize material similar to silicon in its properties, but with different energy response thresholds. So none of the technologies get 4 ticks, and that's the real problem facing photovoltaics and transitioning to this higher efficiency technology where you could get up to a doubling in cell performance by switching to it. So I think that's the major research challenge facing photovoltaics, is to find a material that ticks all 4 of those boxes and can be stacked on silicon. So I'm sure it's something that's going to happen, but it's just whether it's going to take 5 years, 20 years, very much an unknown. So when found, it makes sense to stack 2 cells onto silicon. The first one, you have to do a few things differently, and the second one, you don't have to do much at all, so it's very easy to implement. But as I'll show, the industry's heading towards terawatt sales per year of these panels. So after a couple of years of these stacked cells, you'd be getting plenty of field experience with these other cell technologies. So you just wonder whether silicon's going to be required, because as you stack more cells onto silicon, they absorb some of the photons the silicon cell would have absorbed, so the power output from the silicon goes down, proportionally to the number of cells in the stack. So it becomes less and less important to the power output. So I think eventually the final photovoltaic technology will be a thin film stack, but whether we get it in 2040, 2050, 2060, I'm not sure. But it's the ultimate technology. So costs, which of course have been really important, and this graph here just sort of shows a semi-logarithmic plot, all the published studies of costs and prices of photovoltaics over four-ish decades, as shown there. But the interesting thing is, on this plot, you can fit a lot of the data by a straight line. So for most of the history of photovoltaics, the costs have been costs and prices, which haven't been a big difference. It's been a low margin industry. The costs and prices have been reducing about 7% a year, so that's compounded cost reduction. But all of a sudden, around 2008, something dramatic happened and went on a new trajectory. So at 7% a year reduction in 2020, the solar panels would have cost $1 per watt of output. And in fact, they cost less than 20 cents per watt output. So this dramatic shift around 2008 had enormous impact on the industry. And here's the gentleman responsible, Dr. Zhengrong Shi, my 12th PhD student. But he was inspired with the ambition to establishing photovoltaic manufacturing in China, where he was born, although now he's an Australian citizen. But China at that stage had none of the required infrastructure, so we thought he was very ambitious in his plans, but gave him a bit of a hand to help him out as well. And you can see the cost reductions that have since occurred. 24 times reduction in the average wholesale selling price of solar modules from 2008 to 2020, 24 times. So the modules on the right there are about 300 watts rating, less than half a horsepower. But they would, at 300 watts, they would have cost $1,200 in 2008, so really expensive. But at 20 cents a watt, they cost $60. So something that was really very, well, at 17 cents a watt, it'd be $51. So something that was really very expensive very quickly changed from something very cheap. And it took a lot of people a bit of time to catch up on that development. So some still think of solar being cheap, which is thinking back to the 2008 type era, whereas in fact the costs have been completely revolutionized and are now extremely cheap. And the way Zhengrong triggered this was by setting up in China, and this was the first commercial cell production line established in China in 2002. I was there to help do some of the heavy lifting, cutting the ribbon on the opening ceremony. So we had no realization then that this was the birth of the modern industry and the era of cheap photovoltaics. but that's what it turned out to be. So Zhengrong was CEO of this company that raised 6 million from local companies in China, and he managed to set up this first production line on a shoestring. Like our lab never been all that well funded by international standards, so everything we did was on a shoestring, and that expertise was able to be applied to setting up this first facility in China on $6 million, and some of the people involved from our group are shown there as well. But Zhengrong did well. Germany had introduced a feed-in tariff program, which has really been very important internationally to the development of both wind and solar technology. Just occurred at a very crucial time for the solar industry, in that Zhengrong was able to sell his output from China into the German market, which allowed him to grow very quickly. At that time, there was a lot of interest in Chinese stocks on US markets, so he was encouraged by some of the US investment banks to organize a management buy out his original Chinese investors that had put in the 6 million. They got bought out for 81 million, so they were very happy with the profits they made, and floated on the New York Stock Exchange at the end of 2005. Only part of the company was on offer. He raised 400 million with that small section of the company that was on offer. It was the top technology IPO worldwide of 2005, made Zhengrong the first solar billionaire, and Goldman Sachs, one of the companies involved in organizing the whole thing, made at least 200 million. So that created an avalanche that's been very important to the industry of fledgling Chinese companies looking for US investment banks to repeat what Zhengrong was able to do, listed on the US exchanges. And US investment banks like Goldman Sachs that had done quite well from Zhengrong's listing, looking for fledgling Chinese companies that they could pass off as equivalent of Suntec. So I've just shown there was a rush of listings as soon as these companies could organize. Took about a year for the next listing to get organized, but a rush of listings after that on the US exchanges. The next 5 are shown there in the graph. But part of the due diligence was, because Zhengrong was from our group, had to have people from our group in senior technical positions to show good technology access. And that's what happened with most of the listings that followed. So over 7 billion was pumped into this fledgling industry from US investors between 2005 and 2010. And that's sort of what really kick-started the modern industry. So these companies, 10 of them listed between 2005 and 10 from China. And the 2021 world rank sort of shown there. 6 of those 10 were still in the top 10 in that era, so sort of forming the backbone of the modern industry, just sort of showing how this was so crucial to its formation. So that explains that first 2 dramatic cost reductions. These companies, highly cashed up from US listings. They didn't have to buy second-hand equipment like Zhengrong. They could buy the best European equipment, get into manufacturing. Then they had to sell their product, and that caused a strong downward pressure on prices as they fought for market share. And then, most of the market had been European-based, largely in Germany, but also Italy and Spain bought huge amounts of photovoltaics over those early years. But then, as the market got dominated by these Chinese manufacturers, the European market became less inclined to support these Chinese manufacturers. So China took over responsibility for market development, although unlike the European schemes, it was a pretty closed shop in terms of companies that could supply to it. And so you can see on that chart on the right, upper right, the red region, the bars show the total market in each year in gigawatts peak. So the market last year will be about 416 gigawatts, which is off the chart, as the arrow on the right indicates. But the red just sort of shows the share of that market that went into China. So China became not only the market dominant supplier, but also the major market user. So the growth is great. It lowers the sell prices. The more you make, the cheaper you can make them. And also it has provided non-coal-fired power to China. So the other option would be installing more coal-fired stations in China to support their growing energy demands. But this huge uptake of solar, with now 0.5 terawatt of solar installed in China, a huge amount has offset the need for as many power stations as would otherwise be there. The other thing that's quite interesting that I'll mention is just the introduction of PERC, this battle between the 40-year-old technology and PERC that I showed in an earlier graph. It also had pressure on prices as the incumbent technology tried to stave off the inroads being made by the new technology. The only strategy available was to lower prices. And again, you see this acceleration in cost reduction in the graph on the right due to that competition. So new technology really can have a big impact on prices in an industry like this. So these reducing costs that are shown on the chart on the right there, so getting well below the $1 a watt, which many of us thought was as low as the silicon technology could ever go. That was surpassed in 2012, and getting down to 20 cents a watt, as I mentioned before, in 2020. So by this stage, even though it took a while for many of the more conservative groups to be convinced that these price reductions were real and were going to stay and so on, but the International Energy Agency, which had never been too enthusiastic about renewables, had a complete change of heart in relation to their potential. So in 2020, the first time, they said solar, the new king of energy markets, now the cheapest source of electricity in most countries, and now offers some of the lowest cost electricity ever seen in history. So this massive turnaround as the realization that these cost reductions were real, and solar now did indeed provide much cheaper electricity than other alternatives. And others were even more enthusiastic about the reduced prices, and Ramez Naam termed this phrase, solar future is insanely cheap. So we got this new source of energy that's going to be very much cheaper in producing electricity than anything we've ever seen before. And carbon tracking, the sky's the limit. I believe there's 100 times more potential for energy generation from cheap solar than the global energy demand. So abundance of cheap solar. What are we going to do with it is sort of their approach and things. And the two charts on the right just sort of show type of projections you see for how the costs are going to continue to reduce with time. So large uncertainties in them, but some solar stations have been installed where the proponents of those systems have been offering electricity for 1 cent a kilowatt hour, or $10 US a megawatt hour is equivalent value. And like in Australia, I pay 35 cents a kilowatt hour for my electricity. So one cent is really very insanely cheap, but it's the type of electricity prices we're going to see from solar in the future. We had a bit of a disruption with COVID, but things have recovered now. So we had about a 3-year disruption due to COVID and some other accidents in the industry and so on, but we're back on track with low costs. So just to finish off in the remaining minute or two I have, I'll just talk about the role that solar might play in climate change mitigation as a result of this. So as I mentioned, the International Energy Agency hadn't been too keen on the potential for solar, but in 2020 had a huge change of heart. And their roadmap for net zero by 2050, released the following year, calls for the scaling up of solar and wind rapidly this decade. So the chart on the right just sort of shows what they believe would be desirable for solar. So two things are shown there, the accumulated capacity. So we surpassed 1 terawatt of solar worldwide in 2022, and they thought 5 terawatt would be a very ambitious target for 2030, but something we should really be aiming for. So that's sort of accumulated installed capacity of those figures there. But the other thing is sort of the slope of that graph, the amount that the capacity increases per year. So they believed that the capacity would grow to about 630 gigawatts a year of photovoltaics being installed, and then sort of saturate and maybe decrease after that, which is not in agreement with what some of us more involved in the industry believe. So this is a projection from industry proponents about what might happen. So the two things are shown on that semi-logarithmic graph this time. The blue just shows that accumulated capacity, which is in good agreement with the IEA figure up to the present. but then it projects much stronger uptake. So rather than saturating at about 14 gigawatts projected by the International Energy Agency, the figure here is about 80 or 90 gigawatts, so 5-6 times higher. So playing a major role in displacing carbon and so on from energy generation. And then the orange one just shows that annual installation. So instead of saturating at 630 gigawatts a year, saturates at 3 to 4 terawatts a year of photovoltaic manufacturing. I've just compared the IEA figures there, but I won't worry about that now. The IEA, of course, has been very conservative in its previous predictions of solar uptake. This just sort of shows the straight lines to the right there, just sort of show their expectations for the industry to saturate, prematurely in all cases in the past. So, the industry forecast is likely to be more accurate than the IEA. Also, the Intergovernmental Panel on Climate Change had not been very optimistic about the role of renewables in our energy future, but their attitude changed about the same time. And in their Mitigation of Climate Change report in 2022, they listed all the options that we had for reducing CO2 emissions by 2030. And on the far right, you can see a lot of things that you probably can't read. But the bars just show the likely CO2 emission reductions. And the blue regions are really very important because they're the ones that can be done at zero or negative cost. So you can save money by doing them. A lot of them down the middle there, lower middle, on the right, are to do with transport. So, going to electric vehicles and more efficient vehicles and all that kind of stuff has got enormous potential. But the two important ones are up the top there. And in the blow up on the left, you can see wind and solar got the maximum potential for reducing CO2 emissions quickly, at zero or negative cost. So what's that mean? The chart on the right just sort of shows one of these projections of past CO2 emissions and, a possible trajectory of getting us down to zero on a finite timescale. And when I saw this is quite an old chart, but I've never seen one illustrates things quite as well. It shows the emissions from the 4 biggest emitters and their likely future emissions, given their best efforts that are presently in train to reduce emissions. And you can see there's a pretty obvious problem. The whole budget for 4 biggest emitters, on this chart here, are going to be used up just by the 4 biggest emitters by 2030. So that looked pretty hopeless when I saw it in 2015, but since then we've had these further dramatic solar price reductions. The little arrows there with 1 terawatt solar written beside them just show the impact of installing 1 terawatt a year of photovoltaics upon CO2 emissions if you displace coal from electricity generation or oil from transport. You save huge amounts of CO2. So if you can keep everything else pretty much under control and do these displacement activities with the solar, you can sort of get yourself on the right kind of trajectory. And of course, if you can get up to 3 terawatts a year, you've got even more dramatic scope for reducing emissions. The chart on the lower left just sort of shows projections. So it's expected 2027, 2028 we'll reach that terawatt a year. 400 gigawatts last year, which is 0.4 of a terawatt, but growing quickly. This just sort of shows how a world powered by solar and wind might look. The red are the regions where solar uptake is strong, including this region of the world, around the Indonesian archipelago. And on the one on the right just sort of shows the wind uptake, which is just about diametrically opposed to where the solar is strong, the wind is generally weak. For countries like Singapore, which is great potential for solar but not much land available, one idea that's been investigated by the Solar Energy Research Institute here is floating solar. And mostly it's been installed on lakes and so on now in many parts of the world, but there's been an interest in maritime installation of floating solar. And the chart below just sort of, the bluish, light blue regions show regions, well, the yellow and green regions show region of the world where particularly favourable for maritime floating solar, like out in the open seas. And around the equator, because of the Coriolanus force and so on, you you don't get many tropical storms. So all those grey regions show regions prone to tropical storms. And if you look closer, you might be able to pick up Borneo and Malaysia and Sumatra there. But the red regions of this graph are the regions that have some of the lowest wave heights, maritime wave heights in the world. So this particular region is really good for floating solar because of the quite moderate wind speeds combined with the really low wave heights that make much less challenging to install these systems. So that's the end of the talk. I'll finish there, but I just wanted to impart the idea solar is going to become even cheaper. New technology, which there's plenty in the wings, it accelerates the pace of change. 10 cents a watt modules, already they're selling for 10.7 cents a watt, so we're going to see 10 cents a watt modules, which seemed impossible 10 years ago that we'd get to those type of prices. 1 cent a watt kilowatt hour electricity prices are in the near future. And because of these low costs, for economic reasons, solar is going to play a major role in mitigating global warming. So thanks very much for your attention. And leave sit down, Bree.
Sit down. Thank you very much for the talk today. And it's been a pleasure for me to sit here today with Professor Green, the father of photovoltaics, as you have been often defined. So now we have time for a few questions. So I'm firstly asked to the audience if there are any questions. We have one here. Microphone. Here, second line.
I'll repeat your question if you like.
Okay.
So today, photovoltaics is used as a kind of supplementary source of energy to become.
Yes, they're asking you to go to the speaker up there.
First of all, thank you for a very interesting talk. So today, a photovoltaic source of energy is supplementary. For it to become the major source of electricity, you have to solve the storage problem. And as far as I know, the cost of batteries is not going down as dramatically as the cost of solar cells. So what, in your opinion, will be the future of using solar energy when half the day during night you are not going to have any electricity produced, and during days where the sun is shaded, you don't have a source of electricity? How can you transition to close to 100% photovoltaic energy?
Yes, thank you very much for the question. Yeah, it's quite an important one because it's often asked. But yeah, no, battery costs have been coming down very dramatically. And in fact, I've seen charts which show that it's pretty similar to the rate of photovoltaic cost reduction. And I think further improvements are expected, and people are talking about transitioning to sodium batteries and so on, which offer even lower cost potential further down the track. So Australia last year supplied about 20% of its electricity from solar, and some states even more from solar. But the storage requirements can be reduced in several ways. And one is by installing wind as a complementary source with solar, because in Australia and many other countries of the world, the two are largely complementary, like wind blows mainly in winter and at night when solar obviously isn't at its strongest. So that's one feature. And the other feature is geographical diversity. So, Australia's a big continent, so we can connect regions of Australia that have different wind regimes completely and different rainfall patterns and so on. So by having strong transmission within the network is the other way that you can reduce the storage requirements quite massively. Actually, the main storage that's used on the grid is pumped hydro storage, and that was developed mainly for nuclear energy. Not many people realize this, but nuclear has the same problem, but in reverse. Countries like Japan, where nuclear has to operate either flat out or off, they had to install huge amounts of pumped hydro electricity so that the nuclear could send all its energy into that at night time, and then that got released during the daytime. So Japan for a long time had every nuclear plant was backed up by half a hydro plant in capacity. So, installing hydro is another approach, but I think the uptake of solar is going to be rapidly that, those standard engineering approaches might be too slow. It takes many years to design and install a hydroelectricity facility. Global connection is another possibility. So, there's a group in Australia working actively to connect Australia to Singapore in electricity supply, and there's already connections between Europe and Africa, for example, been there for many years, but strengthening those for getting more geographical diversity into the supply. And there's been talk for years about globally interconnected electricity network. The sun is shining somewhere in the world and the wind is blowing, so you just circulate the electricity from where it's being generated to where it's being needed. So I think there's been many studies done that have just looked at the climate records in terms of wind and solar availability, around the world in intervals as short as 5 minutes, and just sort of showed that it is technically feasible to do a balance of those without requiring anything but, depending on the proponent's choice, pumped hydro, battery storage, global interconnection, and complementarity in terms of wind and solar. So so there's many studies that sort of show a fully renewably powered world is feasible with technology that we have available now.
Thank you. Thank you very much. I think we are ready for the second question.
Good morning. Thank you very much, Prof. My name is Best Koza from South Africa, University of Cape Town. Two simple questions. One is, I would love to hear your comments about the lifespan of these solar cells, as well as the disposal strategies, which I often highlighted as disadvantages of solar energy. And then lastly, just perhaps what would be your top two subfields of solar energy which you think needs more research and further improvement? Thank you.
Thank you.
Okay. I often forget the second of multiple questions, but I'll do my best to remember it. Yes, in terms of lifetime, manufacturers for a long time have offered a 25-year warranty on the solar panels. So that's the type of field life that's expected from the panel. Although recently been a bit of a escalation in lifetime offers. So now one manufacturer's offers a 40-year warranty with degradation of less than 10% in the module over that sort of period. And I think that will only improve as people get better at correlating module design and lifetimes, through field data and better simulations of the packages and so on. So I think you can look at lifetimes of the panels, similar to building materials ultimately. So like 50 years is one goal that has been mentioned in some international programs as a target. So there's no real problem. Of course, in some climates are more severe than others. So India, for example, has been much tougher on the panels than Europe, for example. So design changes are sometimes required for specific environments. The second one about research areas, I mentioned one in my talk, and this is I think the ultimate cell technology, like the silicon cells are limited to 29% efficiency. And manufacturers, the best manufacturers now are manufacturing cells that are 25 to 26% efficient in production, billions of cells a year sort of quantities. But by stacking cells onto silicon, you can roughly double that. So we hold the world record for a solar panel for solar conversion. And while the best commercial panel is 24%, our record for a prototype lab device is 40.6%. So you can look at perhaps doubling by this cell stacking approach. But as I mentioned, the problem is finding a suitable cell to stack onto the silicon, suitable cell material. So perovskites are the hot favorite, but they have had problems with durability. And offering a 40-year life with a perovskite at the moment is just out of the question. So you probably want to match the durability of silicon to have a viable commercial product, I think, with the perovskite. So, but there's other materials that have better stability and don't involve any toxic elements, like perovskites involve lead in a large percentage of their active constitution of the converter. But the problem they have is they don't have the efficiency. But I showed a chart of how the silicon cell efficiency evolved, and it took, gee, how many years? It's from 1940 to 2000, and it took about 60 years for the technology to go from 1% to 25% in efficiency. So with a new technology, the thing about the perovskites, they went very quickly on that trajectory. But with other technologies, it's often hard work to find the route to improve that efficiency. So that's the challenge, finding a material that you can get to these high efficiencies reasonably quickly. So I think most materials, there's probably a path to getting to those efficiencies. It just requires a lot of work to find that path. So yeah, a lot of potential for research there, although a lot of it's unrewarding because you're going to have a lot of negative results before you have a positive result. So the perovskites is very rewarding from a research perspective because there's so many people working in the area and so many people interested in it. But working on these less better known materials is far less rewarding because you're likely to producing negative results most of the time, and no one wants to publish those.
Okay, I'm sure that there will be many other questions, but unfortunately our time is up. So
Wasn't it half past?
Wasn't
it half past?
Yeah. Yes,
thank you very much.
But,
thank you, Professor Green. Thank you, Professor Bruno.
Let's join
Yeah,
me.
I'm afraid I have to draw this plenary to a close as we're running short of time. So I'm sure you have a lot more questions for Professor Green. Please feel free to catch him during the break. Right. Thank you once again, Professor Green and Professor Bruno. Thank you very much.